In this video, I'd like to show you how to solve this integral. Nothing that particular about this integral, and many substitutions will work, but I would really want to emphasize one substitution that is more natural than the others, and maybe pass this intuition to you. That's the most valuable thing in this exercise that we're doing here. Maybe some trigonometric identities. So my first tip to students is whenever they look at a function or an expression that has some physical meaning, is to always try to analyze it for singularities or where it could break down or may be undefined, right? So here, of course, we see right away that it's undefined at x equals a, and in fact, we need more. There's the restriction, so we need, of course, x to be smaller than a. So suppose that let us assume for definiteness that a is positive. Okay, so we need x to be smaller than a, because if it's x is bigger than a, then and a is positive, so of course this will have this square root of something negative, will be undefined. We're in the real realm, and we do not wish to go here into complex analysis. Not that complex analysis is not fun, but it is beyond the scope of this typical course, right? So of course we need x to be smaller than a, and analyzing this part over here, we need x to be bigger than minus a. So the absolute value of x is smaller than a. So that's a restriction in order for this to be defined, and it needs to be strictly smaller because for the square root to be defined, and for strictly smaller so that we do not divide by 0. And actually that gives us a hint of what should we substitute. And so the domain of definition gives us a hint, and so what we should substitute here is x, a, and what I would suggest here, so or cosine or sine would work, but cosine is more natural, and we'll see why. Actually, not the cosine of t, but the cosine of 2t, and we'll see right away why. So I've made a video of how to remember and to derive yourself all the trigonometric identities, and so if you didn't watch it, I do recommend you watch it if you want to remember all the identities and be able to derive them yourself. And what is so nice about this substitution? First of all, it enforces this constraint. Okay, and the second thing is that we'll derive two particularly nice identities here. So the cosine of the double angle is from the identity for the sum of angles is the cosine squared of t and minus the sine squared of t. Okay, and of course, since sine of t plus the cosine sine squared of t plus the cosine squared of t is always equal to 1, then writing the sine as 1 minus the cosine squared of t will give us the identity that this is twice the cosine squared of t minus 1. And this leads us to something nice. This implies that when we take this one, so we equate this part and this, and we shift the 1 to the other side and divide by 2, or we do not divide by 2. So 1 plus the cosine of the double angle is cosine squared of t. And it makes sense, right? Because cosine is always bigger than minus 1, so 1 plus the cosine of whatever it is going to be non-negative, and everything that is non-negative is square of something, and here it's nice, it's the square of the double angle. And something similar happens if we write this identity. So the cosine of 2t can also be written. Just let's exploit symmetry here. So if we write now 1 minus the sine squared instead of the cosine squared, we get 1 minus twice sine squared of t. So we get that. And now if we shift the sine over here and subtract the cosine, so this would imply this identity, and we write it here. So all of it implies that 1 minus the cosine of t. So again, 1 minus the cosine of 2t, since the cosine of 2t is not bigger than 1, then this is also a positive expression. Oh, of course, we forget twice. This is a positive expression. It's a square of something, and here it's nice. It's sorry, this is the cosine squared of t, and this is twice sine squared of t. Yeah, so we got that, and those identities are very nice and useful, and we'll see how they turn this integral into a particularly nice one. So those two identities are really useful: 1 plus the cosine of double angle, and 1 minus the cosine of a double angle. And it can be written for arbitrary angle, of course. So 1 plus the cosine of alpha, we could say, is twice the cosine squared of alpha half, and the same 1 minus the cosine of alpha is twice the sine squared of alpha half. Yeah, definitely, now you remember. Hopefully you'll remember those useful identities, or at least remember that 1 plus cosine or 1 minus the cosine is something that is useful. So, okay, so this domain of definition gave us a hint of what should we substitute. And now let's see, as we make this substitution, how nicely things turned out to be. So on upstairs, we're going to have, so when we take x to be a, I'll do it once, a plus cosine of 2t and plus a here. So we can take a outside here, and basically we're going to have 1 plus the cosine of the double angle. So it's going to be twice, and here we're going to have the cosine squared of t. And similarly downstairs, by the same argument, we're going to have a minus the cosine of the double angle. So we're going to have sine squared, and this is particularly nice because we're taking the square root. So what we're going to have upstairs is 2a, and here it's going to be the cosine squared of 2t, and downstairs we're going to have 2a sine squared of t. And then note how this is being reduced nicely, and we have the square root, and now we need to compute dx. So if x is that, then dx is going to be, so the derivative of the cosine is minus sine, so it's sine of 2t, and we have the internal derivative, which is 2, so it's going to be minus 2a and sine here, so we need to multiply by minus 2a and sine of t. So I'll write sine of t, sine of 2t, as sine of t times the cosine of t, actually twice. This is identity for the sine of double angle, so we're going to have 4a here and dt. So now look how nice things turn out to be. So strictly speaking here, we need to be careful when we are taking the square root, because when we take some varying expression, say, I don't know, so some z which is a variable, and we take the square root of z squared, so z squared is of course positive, and so the square root of z squared is defined by, in order for the square root to be defined, there are two choices, it's called branches, but the square root should always be positive, that's the default choice. And so this has to be actually the absolute value of z, because if z would be minus 3, for example, so minus 3 squared is 9, but so strictly speaking, for negative z, when we take the square root of minus 3 squared, it's not minus 3, so it's the absolute value of minus 3. And so strictly speaking here, as we take the square root, I want to to direct your attention that strictly speaking, when we write this, so let me write this integral. So we're going to have here, so it's going to be cosine of t and sine of t. These should be in absolute value, and times, so it's going to be minus 4a, and here it's going to be, what we have is just sine of t, which is nice because we will be able to reduce it, and here it's times the cosine of t dt. Okay, so why is it justified to ignore the absolute value here? Well, because again, if this is x, then let's see what is t. So t would be half arc cosine of x over a, and the arc cosine, the typical definition, there are many choices, but the standard choice, just as we choose the positive square root, we choose the arc cosine to return values of sharp angles for definiteness, and therefore when t is a sharp angle, we're actually taking half of this, so the cosine over sine is going to be positive, and therefore it's justified to ignore here the absolute value. But it's an important point that I wanted to make, and therefore we're going to have the cosine squared here. But look how nice, because we have an expression for the cosine squared, right? So if the cosine squared is 1 plus the cosine of double angle divided by 2. So this integral, let me write that this equals, so it's going to be minus 4a, and instead of the cosine squared, I'm going to write 1 plus the cosine of 2t over this 2, and this is dt, and okay, so let me write this as minus 2a, and let's just write the integral. So here we're going to have t, the integral of 1, and plus, so the integral of cosine is sine of 2t, and we need to divide by the internal derivative, which is 2, so it's over 2, and plus a constant. And now if we basically we can now plug in the value for t. So t is, I remind you that it's half arc cosine of that. So we're going, and minus 2. So we're going to have, so it's going to be minus a times arc cosine of x over a. That's with that, and minus 2 here will be reduced, so it's going to be minus a, and here sine, it's sine of twice, but sine of arc cosine. So it's going to be sine of arc cosine of x over a here, and plus a constant. And so now we can, if we wish, so let's get back to this integral that we had. So we had this integral, the x, so it's x plus a over a minus x dx. So it's going to be minus a times the arc cosine of x over a and minus a. So here actually this can be written as 1 minus the square root of cosine squared of this arc cosine, and the cosine of arc cosine is just the expression that is inside. So it's going to be square root of 1 minus x over a, all of it squared, plus a constant. So finally we can push this a into the square root. So we're going to have minus a arc cosine of x over a minus the square root of a squared minus x squared plus a constant, and that's the answer. Yeah, hopefully I didn't make any computational mistakes. Seems to be just right. Yeah, the integral of cosine is sine. Yeah, seems good. But if I made any mistakes, that's an exercise for you to find them. Just kidding. Okay, so another thing that I wanted to show you is where this intuition is actually quite useful. So let us take something simple and well known, and just this example. So of course you know that the integral of this is going to be the arc sine. So, but suppose that we didn't know it, right? And we'll see how to derive it. And so we see basically that here x to be, it needs to be in an absolute value smaller than 1, and so we need a function that is, it would be smart to substitute. So a bad choice for x would be something like 2 plus say e to the power of t, right? E is a non-negative function, but that's a choice that doesn't make any sense, because this function is going to be always bigger than 1, and so we'll be here with a complex expression that is undefined, at least is beyond the scope of the statistical course. So of course that's a bad substitution. We need to substitute something that this would be defined, and so of course that's a bad choice. And an actual choice would be here in taking into account this domain of definition to try x to be sine of t. Of course, knowing the answer is in a way cheating, because we know what we're supposed to have. But see how simply we can solve this integral without, because previously we deduced it from a table because we knew the derivative, we computed the derivative of the arc sine, and we saw that it is this. But if it was the integral to begin with, so if we substitute x to be the sine of t, so we're going to have here, so it's going to be 1 minus sine squared, it's the cosine squared, and taking the square root, this is the cosine of t. And again, we need to be careful because here t is the arc sine of x, and the arc sine is again defined in a way that, at least the standard choice, such that it will return a sharp angle, and for a sharp angle this is positive, so we can ignore the absolute value here. So it's 1 over that, and we, of course, the x is going to be, so the x is going to be cosine of t dt, and the miracle happens again. So it's cosine of t dt, the cosine goes away, and so it's t plus a constant, but t is the arc sine of x plus a constant. So what we see here is that the domain of definition of the function can suggest, or at least give a clue to what substitution we should try, is not just a mere coincidence. And so I hope this was somewhat intuitive, and it was beneficial for you to watch this. So hopefully I transferred some intuition, and thank you for watching, and thank you for choosing this channel.